Hello and welcome to the final part of lesson 15. In this last video we're going to look at one further example of characterizing a viscoelastic liquid, this time in the context of inkjet printing. Inkjet fluids have to be very carefully formulated such that they are jettable, that is to say that they can be printed successfully by an inkjet printhead and give a high print quality. Typically, inks are viscoelastic, but the levels of viscoelasticity are smaller than for polymer melts and for concentrated polymer solutions. The fluids tend to remain viscosity dominated at very high shear rate, up to tens of thousands of reciprocal seconds, but with significant elasticity above a few hundred reciprocal seconds. Different colour inks have to behave in essentially the same way, so it is useful to have a criterion, typically a single relaxation time, that inks have to meet in order for them to be known to work. A key challenge is being able to access the viscoelastic response at very high shear rates, hence a different rheometric approach is used, one of high frequency squeeze flow rather than rotational or capillary flow. So, as before, let's start by stating some aims, by discussing some uses, and then introducing some methods for this characterization protocol. So our aims this time around, again, are to quantify the linear viscoelastic response of an inkjet fluid and to obtain a single relaxation time from that linear viscoelastic response that can be used to characterize the fluid, to generate a pass-fail criterion or to work as quality control. So, in terms of uses, what we want is an easy way of judging whether or not different batches of ink are going to work in our printhead. So what we want is a nice, easy criterion that we can quickly measure that gives us a very, very good idea, perhaps not a complete idea, but a good enough idea, as to whether or not a fluid is fit for purpose. So this allows us a quality control measure between different batches of inkjet fluids or between different colours of inkjet fluids, because remember, you need to have yellow, magenta, cyan and black typically at minimum in an inkjet printhead in order to make a colour image. And in a lot of commercial printers there's a lot of in-between shades as well, and they tend to also include a white. So we need to make sure that across that whole range of different colours we have fluid consistency. So in terms of characterization method, we're going to do something a bit different this time. So rather than do rotational or capillary rheometry, we're going to use a rheometric method called high frequency squeeze flow. And so it's a dynamic method where we're oscillating the sample, but rather than shoving it through a capillary or rotating it within a cuvette or cylindrical device, we're squeezing the fluid up and down and measuring that squeeze response. The instrument that we use for this is called a piezoelectric axial vibrator, or a TREPAV, and they're amazing instruments to allow very, very high frequency measurements to be taken. And if we think about inkjet printing, inkjet printers typically print millions of droplets of ink every second and operate at incredibly high frequencies. So we need viscoelastic data in the same frequency range as the range of frequencies that a printhead works in. And this is the only instrument that allows us to do that. So the first thing we're going to do is to look at the viscous and elastic modular behaviour as a function of angular frequency. So we're going to do an oscillatory frequency sweep, add a fixed strain in the linear region. So it's a very, very small strain. It's not even single percentage figure strain. And these are the data that we get. So on the y-axis, I'm plotting my modulus. My viscous modulus there in kind of salmon pink, my elastic modulus there in blue, both plotted as a function of angular frequency. Now look for a second at the range of angular frequency that we can interrogate. We're not talking 10 or 100 reciprocal seconds, we're talking angular frequencies up to about 10 kiloradians a second, which is very, very high. And these are the frequencies typically that would be operating at in the commercial printhead. If we examine the data, we can see there is a range of angular frequency over which there is clear viscosity dominance. So G double prime here is far greater than G prime, an order of magnitude or more. Furthermore, we can see that the ink remains viscosity dominated over the entire frequency range, but that at higher frequencies, elasticity plays a very, very important role in the rheological response of the material. It doesn't dominate it. There is no crossover frequency. The crossover frequency is above 10,000 radians a second, outside our data range, but we can see that elasticity will affect the material response quite significantly. So once we've got these experimental data, let's obtain a relaxation spectrum and compare the predictions of G' and G" using that relaxation spectrum to our experimental data. So the equations that we'll use are those from Maxwell, and we've seen these expressions a few times now, G' and G" as a function of Gi and lambda I and our angular frequency omega. And a relaxation spectrum analysis shows us typically that 5 relaxation modes give a reasonable fit to the experimental data. And there on the board is experimental data compared to the theoretical fit. And we can see the solid lines there are due to the prediction of G' and G" using those 2 equations. And the symbols, the open symbols, are the experimental data. And so 5 relaxation modes is pretty good. It gives us a good quantitative fit to these data. The problem, though, is that if we're looking for an easy pass-fail criterion, a single figure that says, is this ink likely to work or not, which of these relaxation times do we look at? Do we look at the long relaxation mode, the short relaxation mode, some combination of intermediate relaxation modes, or some kind of average? It's very hard to say. 5 relaxation modes gives us a good fingerprint, and we can maybe pattern match that fingerprint to other fingerprints, but that's a little more complex than just saying, well, we've got a relaxation time threshold here of a certain number of microseconds above which an ink won't work. So can we look at these data in a different way to try and get a criteria such as that? Now, when we talked about polymer solutions, we saw that we had 2 of the simplest models that were molecularly derived, the Rouse model and the Zimm model, and these were able to describe G' and G" behaviour of solutions in different concentration regimes. So let's start by seeing what the Rouse model can do for us in terms of these experimental data. There on the board I've put the equations that describe G' and G" resulting from the Rouse model. Now, we said when we initially saw these equations that they're very similar to the Maxwell equations. If one looks at the equation for G' in particular, we can see that it's almost identical to Maxwell, aside from the fact we've only got a single G0 value rather than a spectrum of GIs. For the viscous modulus, we also have solvent contribution added into there with eta S omega. If we think of the relaxation times in these models, we can see we do indeed have a spectrum of relaxation times, lambda J, where J goes from 1 to the number of modes n that we're using. However, the final equation on the right-hand side at the top of the board reminds us that each of the relaxation times can be linked back to a single relaxation time, the Rouse time, lambda r. So let's see if these equations can fit our experimental data and see whether we can make use of the Rouse time to act as this pass-fail criterion. So there on the board, I've again plotted the experimental data as the open data points, and the solid lines this time refer to the predictions of the Rouse model for both G' and G'. And we can see that the fit isn't as good as it was for a 5-mode relaxation spectrum, but it's not bad. And these values on the board are what I use. So we had a modulus of about 85.5 Pascal and a Rouse time of 11 microseconds. A single relaxation time. Now this is very, very useful because again, if we compare different types of ink, different colours of ink, or between different batches of the same colour of ink, maybe one of the things we can establish is whether or not a Rouse time of 11 microseconds gives us a pass-fail criterion for whether an ink is going to jet or not. If we do this type of experiment and found we've got a Rouse time of 150 microseconds, for example, that might be enough to raise a warning flag to say that batch of ink is not fit for purpose. Reformulate. And so it's very much easier to make that judgment using that single time rather than it is with a spectrum of 5 different relaxation times. So let's just summarise with a few key points. What we've done this time again, is to characterise the linear viscoelastic response of an inkjet fluid, but at very, very high frequency. We initially obtained a 5-mode relaxation spectrum that fit the experimental data very, very well. Very useful, but hard to generate a sort of a pass-fail criterion unless we go down the pattern matching path. We then looked at a simple molecular model, the Rouse model, and it fitted the data fairly well, not as well as the 5-mode relaxation spectrum, but it gave us a single relaxation time result that we could potentially use as a pass-fail criterion for quality control for this batch of ink.